The universe continues to amaze, and one of the most intriguing objects observed recently, the interstellar object 3I/Atlas, has once again gained prominence in the scientific community. Originating from an unknown star system, Atlas has become the focus of a new study conducted by the Keck Telescope in Hawaii. The importance of this investigation lies in the rarity of interstellar objects, with Atlas being only the third detected. Although at the time of recording, the object was temporarily hidden behind the sun, analysis of data collected during its closest passage provided crucial insights into its chemical composition, raising new questions about the formation and evolution of celestial bodies outside our solar system. The opportunity for this study arose when 3I/Atlas, classified by many as an interstellar comet, was approximately 2 astronomical units away from Earth. Using the power of the Keck Telescope, astronomers focused on analyzing the spectrum emitted by the object. Spectrums are a fundamental tool in astronomy, allowing us to identify the chemical elements that make up celestial bodies through the light signatures they emit or absorb. The data obtained during this observation window, which occurred on August 24th, 2025, were subsequently published, detailing significant discoveries about Atlas's material ejection. The researchers' main discovery was the clear detection of spectral signatures of 2 elements being actively expelled by the object, cyanide, CN, and nickel. These emissions were clearly marked, indicating considerable activity. It is important to note that the emission of these gases was well localized, occurring in an anti-solar direction. This phenomenon suggests that the object was being heated on one side by the sun, and the gases were released on the opposite side, a physical behavior considered normal and expected for comets approaching a star. This reinforces that, despite its alien origin, 3I/Atlas exhibits cometary dynamics comparable to those occurring in our solar system. In addition to the nature of the detected elements, astronomers were able to quantify the distances at which these emissions were occurring from the object's nucleus. A strong cyanide CN emission was observed extending up to 840 kilometers from the object. In a more compact form, gaseous nickel emission was recorded at a distance of 200 kilometers from the nucleus. At the time of the observation that generated the data, Atlas was 2.75 astronomical units from the sun. These spatial details help to trace the object's heating and degassing profile under stellar heat, providing important insights into cometary chemistry models. The presence of gaseous nickel in an interstellar object is particularly noteworthy. This chemical characteristic suggests similarities between the formation processes of 3I/Atlas and the second interstellar object discovered, 2I/Borisov. The increasing detection of nickel in interstellar comets thus offers a new avenue for tracking the chemistry and metallicity of their parent star systems. However, 3I/Atlas demonstrated a crucial difference compared to typical comets in our solar system and 2I/Borisov itself: the absence of iron emission. Some scientists speculate that iron emission may only be triggered at greater heliocentric distances, and that the chemical difference observed now does not rule out the possibility of normal behavior at other stages of its journey. These Atlas measurements of metallicity and volatile chemistry are not just point-in-time information. They are vital for advancing new insights into the radioactive evolution of elements under different stellar conditions. The mechanisms governing nickel emission may differ substantially between comets in our system and interstellar comets, but the spectrum analysis provides a necessary roadmap to discovering the parent star that gave rise to 3I/Atlas. Future projects, such as the Vera Rubin Observatory, are expected to detect significantly more interstellar objects, allowing scientists to construct robust statistics and behavioral patterns that are not currently possible. The importance of this research is compounded by the extreme scarcity of data on bodies outside the solar system. Atlas is, after all, only the third interstellar object ever discovered and observed. 3 objects are insufficient to construct statistics, create reliable models, or establish universal behavioral patterns. However, this object represents the first real opportunity to study an ISO over an extended period of its passage by Earth and the Sun. Therefore, every piece of spectral information obtained, whether it's the presence of cyanide, the detection of nickel, or the momentary absence of iron, contributes invaluably to understanding how these cosmic wanderers form and behave. Although it is passing behind the Sun and is currently invisible mid-October, Atlas is expected to reappear in about 15 days, allowing new observations and image collection. The object will continue to be closely monitored by several space missions currently orbiting or on trajectory toward Jupiter, including the Juno and Europa Clipper missions, which will inevitably record data from the interstellar object. While the European Space Agency has already released images captured by probes such as Mars Express and TGO, other agencies, including NASA subject operation restrictions, await the release and analysis of their data to expand our knowledge of the behavior, trajectory, and composition of this remarkable visitor from deep space. The detections of nickel and cyanide in 3I/Atlas confirm that this is an intriguing object, but its behavior fits within the largely normal range observed for comets in our cosmic neighborhood. The in-depth study of the gases ejected by Atlas solidifies its role as one of the most crucial bodies for contemporary astrophysics, acting as a chemical bridge for understanding the diversity of materials and the formation of stellar systems throughout the galaxy.